So, thank you for the introduction. I am an astronomer here at the University of Canterbury, where I do research on some of the most explosive phenomena in the universe, and teach some courses. So today I'm going to be spending some time talking about the very explosive stuff that I study in the universe. But before we get on to thinking about that, it's always good to get some perspective on the nature of the universe. So if you were to go outside on any given nice clear night and look up, you would see something that would look fairly similar to this, where we have the great big beautiful Milky Way stretching across the sky with all of its stars. And in the top left, we have the Large Magellanic Cloud and all the other stars scattered around. Now, one of the really neat things with this view of the sky is that if you went a few thousand years into the past and grabbed someone and brought them up there with you, they would recognize pretty much the exact same stuff in the sky. The sky that humanity has seen has pretty much been constant. There'll be some things that would seem quite peculiar to them, like the Trigg station sitting atop OTY Mount John. They'd be pretty freaked out by some bright lights moving very rapidly across the ground. And there would be some dots in the sky that are just slowly moving, that look like streaks in these images. But we'll get to those streaks in a bit. So to get some sense as to what the universe is and what it's made of before we think about how it explodes, let's think about the giants of the universe. So for the most part, these stages that all of the activity in the universe plays out on are in these great big giants, the galaxies, where they are comprised of extremely numerous number of stars. And in this case, we have the Andromeda Galaxy, which is the nearest galaxy to our own Milky Way. And because it's so close to us, telescopes like the Hubble Space Telescope can take such clear images of it. We can take any point in this galaxy, or at least some points of it, and blow that up to see what it's made of. And this blow up of that section of the galaxy, we can see that it almost looks like a beach for all of the stars that are sitting there. But this isn't the limit to Hubble's resolution. We can take another section of this and blow it up further still. And you can see that there are just stars all the way down. These big galaxies are made out of an enormous number of stars. For the Andromeda Galaxy, we expect there's somewhere around 1 trillion stars that make up its entirety. And that's a fairly standard number. Smaller galaxies might be on the order of hundreds of billions of stars. So these things are enormous. They're made out of stars for the last part, but they're also all over the place to the point where they're almost as numerous as the stars in this image. So if we were to take Hubble and instead of pointing at the Hubble or at the Andromeda Galaxy and point it at a patch of sky that seems completely blank, what we find is it's filled with galaxies, where each point in this image is a galaxy that is extremely far away from us. So this is a section of the sky that is much smaller than the full moon. And as we zoom out, you can really see just how many galaxies are sitting in this tiny section of the sky that if we were to take it and stretch out over the enormity of the sky, you can quite easily begin to see that there are too many galaxies and too many stars in our universe. And again, this image is pretty static. If you were to come back in a couple million years' time and look at this, it would pretty much look exactly the same. The universe on this scale evolves very, very slowly. So it's kind of a challenge to work out how we can say galaxies change over time. So for example, these big, lovely spiral galaxies, they will spin once every few 100 million years or so. So that's kind of like a daytime for a galaxy. So there's no way a human could live their life and see changes play out on this big cosmic scale. So a good question is, how do we understand how these really big things change with time? And to answer that, we can first turn to the namesake of this lecture series, Professor Beatrice Hill Tinsley, who was a phenomenal astronomer and was renowned for going to lots of different areas of astronomy and synthesizing information to work out how stuff can all fit together. So she was able to piece together a history of how these galaxies evolved over time and kind of pioneered this understanding of these gigantic beasts. And the way that we can infer how galaxies evolve over cosmic time is through two things. We can use our knowledge of physics and do simulations of the world around us, because in simulations, time is just something you can freely change. So you can run time forward at millions of times the rate that we would see it pass by, and actually watch these things play out according to the laws of physics and a time frame we can understand. The other thing, aside from simulations, we can use is the fun fact that light takes time to travel places. So light travels at around 300,000 kilometers per second. So that means that very distant galaxies, or any object that's far away from us, it takes time for that light to reach us. So if we were to find groups of galaxies and observe them at different distances away from us, we could start to build a picture of how galaxies change over time, little snapshots throughout the evolution of the universe. So this may seem a little weird, but it's pretty much exactly the same as how we look at evolution with organisms on Earth. We see little snapshots in the fossil record and string those all together. So with these two things, we can work out how the great big scales of the universe change. These are scales that no human will ever see play out. But there are things in the universe that play out on a much more manageable time scale. So let's think of some nice historical examples. So first of all, imagine yourself as an Egyptian astronomer a few thousand years ago. You're looking up at the night sky, and there is one star in particular that's become quite interesting to you, this star called Al-Ghul. And the reason it's become so interesting is that it appears to change its brightness every 2.8 days. So at this time, we all believe that the sky has some kind of power over controlling our day-to-day lives. So something in the sky that's changing must have some influence on what the days are going to be. So we go away and think about it for a while, and we conclude that Al-Ghul tells us which days are going to be lucky and which days will be unlucky. So this was the state of astronomy a few thousand years ago, but there were things in the sky that we could see and we could document them changing. If we fast forward a little to be ancient Chinese astronomers in 1054, we would notice that there would be a new star that appears in the sky. And unlike the other stars, it sticks around as the sun rises. It's so bright that it rivals the brightness of the moon. And we can see the star in the night and day sky for the next 2 weeks until it fades away. And then we can still see it in the night sky for the next 3 years. So all very excited about finding this new object, you would go away and write the following, where this describes that you have discovered a guest star, a guest that has appeared in our night sky, and like all good guests, will leave at some point. But in this case, there were still prevailing ideas that the sky had some meaningful control over our day-to-day lives. So you would seek to try and attribute it to some war or changing of kingdoms. So this is our first really big, interesting thing that changes and disappears. We now know that these guest stars are supernova, and the last one that was observed, observable by the human eye, was in 1987. Supernova 1987A went off in the Large Magellanic Cloud, and it was visible to the human eye. And again, a really cool thing about this is that it was discovered by New Zealand amateur astronomer Albert Jones, who worked out of Nelson, and over his lifetime conducted something like 500,000 observations of variable stars and other changing objects in the sky. His dedication was extreme, and when I was in Nelson to give this talk, I had the great pleasure of hearing numerous stories about Albert, and by all accounts, he was a fantastic person. So it's very good because I have him here as kind of the limit for as far as humans can go at seeing changes in the night sky. To be a good astronomer like Albert would require you to be up every night. It's clear, take observations all through the night, and be very dedicated to what you're doing and have superb eyesight. I would fail on a number of those things, so luckily astronomy has evolved a little. So nowadays, we generally use detectors on the backs of cameras, and for most of my work, I use cameras that are sitting in space to try and find things that change in the night sky. So an example of this is a object that was observed by the Kepler Space Telescope here on the left. And then on the right, we have a series of images looping. Can you spot something that's changing in these series of images? I want to volunteer where they see something changing. Yep. Perfect. That is exactly right. So up in the top right here, we can see there's a flash of light that then fades away. And this event is incredibly bright. You would really need to be an idiot to not spot it going off in the night sky, which was fortunate because I was the one that discovered it. So this object is known as a dwarf nova. We'll come back to those ones later. But this is, again, very, very bright. It's uncommon for objects to be this bright. A better example would be something from TESS, the Transiting Exoplanet Survey Satellite, where we have one image on the left and another on the right. And these images, we have what should be a lovely merging galaxy in the middle, and around it a bunch of stars. You might be straining your eyes trying to spot where the change is here, but it's really difficult, probably even impossible, because the galaxy and stars are just so bright. So what astronomers tend to do is we take one image, say the one on the left, and we subtract it from the one on the right to get what we call a difference image. So in the difference image, we have a bunch of stuff like the stars around the edge. They look kind of weird and not like stars anymore. That's just because they didn't quite subtract out perfectly, because stars are gross like that. But you might be able to see something else sitting in the image that's a little more defined. So right in the center, there is a nice compact blob of light. So this was a supernova that went off in 2020 that was pretty interesting because we caught it exploding just as it exploded. So this was known as supernova 2020 FQV. And we're so interested in this that my group decided to trigger Hubble to spin around and observe this just after it exploded to try and work out what actually happened. So in a nicer image of this galaxy, you can see the beautiful merging galaxy there, and then down the bottom is where FQV turned up. And with these observations that we collected, we're able to kind of piece together the history of the supernova, what actually exploded and how it exploded. So this is the crux of the work that I do. We spot something, we observe it as much as we can, then we try to piece together its history. So those are the methods we now use to look for explosive stuff in the universe. So if we were to go and try and observe everything that explodes in the universe, we can ask ourselves two questions to try and categorize everything nicely. So the first question we can ask ourselves is, how bright is it? This is a very easy question. What is the intrinsic brightness of the object? Is it just very bright, super easy to see, or is it perhaps faint and not so obvious? The other question we can ask ourselves is, how long is it visible for? It could be one of two options again, very fast, if you blink, it's gone. Or it could be super slow, like the guest star of 1054, where it just hangs out for a number of years before disappearing. In all of these cases, once they're gone, they're pretty much gone forever. So we can use these two questions and the answers we get for them to define something we call the time domain. And you might think this seems suitable for a police phone box to go flying through. But instead, we have something even more exciting sitting in here, a set of axes. Wow. So the first one is the y-axis, which is brightness. Wow. way better than Time Lords. What do you think the x-axis is going to be? Time, good. So we have the lifetime of the event on the x-axis. And we're going to do some weird steps along here. We're going to start at 1 minute and go to 1 hour, go to a day, 10 days, and 100 days. So these weird steps are more or less logarithmic if you're familiar with plots or with that scale. So to make sense of this plot and where things are going to end up, in the top right, objects will be bright and very long-lived. On the bottom right, they'll be faint, but also long-lived. Bottom left, they'll be faint and fast. These are definitely the hardest objects to ever spot because they just kind of flash and they're gone. And the top left, they are bright and fast. So these are a little bit easier to see because they're extremely bright. So what we're going to do now is kind of step through the time domain, plonk some objects down there and see what we can see. So the first thing we'll think about is probably the most familiar object to everyone, a core collapse supernova. Now this is a case where you have an enormous star that's at least 8 times more massive than our sun. It's reached the end of its lifetime. It's turned into this great big red giant star, and it will just collapse down onto itself. And right at the center of the star, it'll be crushed down to make something called a neutron star, and the rest of the material bounces off that neutron star and flies out into space at incredible speeds. To get a sense of what this might look like, here is a nice little video from some images that Hubble took of a nearby core collapse supernova. So as we zoom into this galaxy, keep in mind that all the points of light that you're seeing are individual stars. So this bright flash and fade away lasts just a couple of weeks. And in that moment, this one star easily outshines all of its neighbors around it. So these core collapse supernova are very explosive events. And if they're within, say, 100 light years of us, we're dead. As a simulation of this, we have the red giant star. It'll collapse on itself, as I mentioned before, and then explode in the great big explosion. So this is the stuff that would kill us if it were too close. So if you're wondering about practical applications to this work, we can work out how far away things need to be before we're safe. In this case, all this stuff that's flying out is carrying with it all of the materials that this star had created throughout its lifetime and had created in the brief moment during its explosion. And as it expands into space, it'll make something called a supernova remnant, where here we have the remnant of the Crab Nebula, which we saw before as supernova 1054. So humans have been observing this for an incredible amount of time, and we've been imaging it for an enormous amount of time as well, to the point where we can see it actually expand over the decades. Now, the stuff that's leaving a supernova is traveling at, say, 10,000 kilometers a second. So it's very fast, very energetic. But right at the center of the Crab Nebula sits a neutron star. So these are incredibly dense objects, only about 30 kilometers across. It's often said that if you took a teaspoon of neutron star and dropped it on the Earth, it'd sink through the ground and find its way to the core of the Earth, just because the mass is so large. So these objects are pretty interesting, very dense, and they can do some fun stuff, which we'll look at later. So that's a brief run through of the core collapse supernova. The next thing on our list is another supernova, the thermonuclear supernova. So these ones are brighter and generally more useful. So here we have a thermonuclear supernova, or a type 1a supernova, going off in a nearby galaxy. And you can see that it is incredibly bright because this one exploding star is brighter than an entire galaxy of stars. So as these things are so bright, it means we can see them incredibly far away from us. And the other cool thing is that we know how much energy these stars explode with. So we know how bright they should be. So if we measure how bright they appear to us on the sky, and we know how bright they should be, we can use that information to calculate distances to them. So we use these thermonuclear supernova to actually map out distances in our universe and work out how it expands over time. And that's a very, very useful thing for these exploding stars. And to the level of precision that we understand them now and measure the universe, we have some problems with our understanding of these stars. In all instances, we have a white dwarf, a core of a star like our sun after it's died. It's made of carbon and oxygen. And if it eats too much material from a friend, it'll blow up. So for every case, these thermonuclear supernova come in pairs, but there are two ways that you can make them blow up. The first is the single degenerate case, where we have a white dwarf sitting in the center, and it steals material from a neighboring star until it reaches a magical mass limit and it blows itself up. And this explosion is what we're able to see from these enormous distances. So that's one way to make a thermonuclear supernova. Another way is if we take two white dwarfs and they get too close together, they start to feed material onto each other until they hit that magical mass limit again, which is 1.4 times the mass of the sun, and it ignites and blows up. So this seems cool. We just have two ways to make these explosions happen. No problem with that. The trouble is if there is a change in brightness by either way that these make supernova happen. Because we use the brightness to measure distance, if our brightness is wrong, we're making mistakes in our measurements. So this is a large part of the research that I've been involved with, is understanding what ways you can make a thermonuclear supernova. Back to the time domain. So as we go through this talk, there's one thing I hope you keep in mind and remember, and that's astronomers are terrible at naming things. So we have two types of supernova. The next thing we're going to have is called a nova. So these can come in a few different flavors. The one that we'll talk about for the most part is this one here, where we have a white dwarf sitting at the middle. Instead of a star, it's stealing material off of a brown dwarf, which is just like a supersized Jupiter. And this material falls onto a disk that's orbiting around the white dwarf. And every now and then, this disk will get so hot and dense that it will emit an enormous amount of light that we can see. You've actually seen an example of this dwarf nova way back at that Kepler video. So that flash of light you're seeing in the top right was from one of these disks getting really hot and bright. Other types of nova are just where you have little pockets of thermonuclear detonations happening on the surface of the white dwarf, but it doesn't entirely detonate. Okay, so we have supernova and nova. Any guesses to what we might have next?
Micronova.
Micronova. Close. I like nova. Let's continue with nova and say kilonova. So this object, aside from being horrendously named, is one of the more recent ones that we've been getting to understand. So in 2017, we discovered one of these objects that was associated with a bunch of other cool stuff. There was a gravitational wave event that propagated through space, bending and stretching everything as it went, which was detected by two detectors in America. And the gravitational wave people said, something might be happening in this part of the sky. So then every telescope started searching that very large section of the sky until they came across what might have been causing it. But another thing that we spotted with these kilonova is a gamma ray burst, which is a very, very powerful burst of energy. You could imagine taking the entire energy that the sun will produce over its 10 billion year lifetime and compressing that down to a few seconds and then beaming that out into space with just a few degrees either way. Now, these are incredibly powerful, so we can see them from enormous distances, but they're also incredibly deadly. So it's very good that they're beamed in such a small angle. But the takeaway from this is that if one was beamed at us, we don't need to worry, because by the time we knew, it would have been too late. So back to the gravitational wave. This galaxy was the one that they came to and saw that there was a new star sitting inside this galaxy. And then once it was detected, pretty much every telescope in the world spun around and looked at this for the next few days. So this event lasted for around about 6 days in optical light, and then some days afterwards in different wavelengths. And it was a very interesting event because we were able to work out all of these different things that were connected together and piece together what actually happened in enormous detail. So this thing is known as gravitational wave 170817. Again, we're very good at naming things. So what happened here were we had 2 neutron stars. So those things sitting at the center of the Crab Nebula, if you have 2 of them and make them spin around each other, they will bend and stretch space because they are so massive. And as they get closer, they will eventually collide and fire out 2 gamma ray bursts on the poles. And then in the middle, we have the kilonova that forms. So this kilonova lasts for about 6 days before it fades away. So it's the fastest explosive thing we've looked at so far. So that's kind of one of the more recently added things to the time domain that we understand quite well. But you might notice there's a bit of a problem here. We've got a lot of stuff on the right-hand side. We've got one thing on the left-hand side, but we have nothing in the middle. So a good question is, why isn't there much stuff happening in the middle? There could be 2 possible answers to this. One is that the universe just doesn't make explosions on those timescales. That seems maybe a little unreasonable. Why would things that explode for lifetimes of 2 days be okay, but something that explodes in 12 hours not be okay? It's perhaps not the case. Perhaps a better answer is that we just haven't searched that area of the time domain as well yet. Most of these things have been discovered with ground-based telescopes. And with ground-based telescopes, when we survey the sky, the best we can do is really only find stuff that changes over, say, 2 or 3 days. That's kind of our limit because the day gets in the way or weather gets in the way, so we can't look for things that change on shorter timescales. So to do this, we need some other instruments. So what I do is I use space telescopes to try and search this part of the time domain. And the 2 space telescopes I mostly use are these 2 here, the Kepler Space Telescope on the left and TESS on the right. So these were both built for looking for planets orbiting around other stars. But it turns out looking for planets leads you to building telescopes that are perfect for looking for explosions. So there are some problems with these telescopes, like Kepler here developed some issues a few years into its lifetime where it just started kind of shaking on the sky. That's because some reaction wheels failed and they needed to use a combination of the sun and thrusters to keep it pointed. But, you know, we're able to overcome some of these problems, but it's still not terribly easy finding explosions in this shaky telescope. So when 2018 came along, Kepler died and TESS was launched, we thought, all right, we can ignore Kepler now and we can use a telescope that's much better. But it turned out that for whatever reason, they didn't quite anticipate that on the orbit that TESS follows between the Earth and Moon, every 14 days it gets blasted by light from the Earth and Moon. So it's not particularly easy to find explosions in data that has massive spikes in brightness every 14 days. But don't worry, it only took several years for me to work out how to get around that. So now we have 2 space telescopes that we can use to search for some of these explosions. So the question becomes, now that we're starting the search, how or what might we expect to find? So there are 2 things two things here that we might expect to understand. One is called a fast evolving luminous transient, where we have a red giant that throws off an outer layer of material, then does a very weak version of its supernova, blows itself up, that material runs out and collides with the stuff it threw off before and creates a brief flash of light. So these types of objects would only be visible for about a day or so before fading away. We have already observed one of them with Kepler, but we need to find more to actually understand what they are. Another pretty interesting question that we might be able to try and answer is the case of disappearing stars. So here we have two images taken by the Hubble Space Telescope of a nearby galaxy. In 2007, inside this blue circle, there's a nice big red star. And this galaxy is so close to us that the star should explode as a core collapse supernova, and we should see that explosion. But when Hubble went back in 2015 and imaged this area, suddenly there is no star. So the question is, what happened to the star? Where did it go if it didn't explode? And one of the best ideas we have is that it just kept collapsing. It didn't stop at a neutron star and it just kept going down further still. Gravity won completely, and we think it created a direct collapse black hole. But we don't really have any observations to support this other than the star was there, then it wasn't there. If we wanted to see kind of the chaotic light that would be emitted as the star is falling in on itself, we would need telescopes like Kepler and TESS with the rate at which they take images every 30 minutes or 3 minutes to see what might be going on in these cases. So those are two examples of something we might find in the time domain with these two telescopes, and they would sit somewhere around here. So that would make this simplified time domain figure a little bit better, not so empty. But those are just two possible examples. The thing that I'm most excited about in searching through this data is coming across objects that we don't know exist and have no idea that they might exist. So since it's pretty much a completely new time domain that we're searching, it's a little unknown of what we might find. So we have these two views of the universe. We have this universe that is there, it is static for an incredibly long amount of time from our perspective, and we need to use simulations and observational tricks to understand how it changes and evolves over time. Then on top of this universe, we have this other very dynamic universe, which is always changing, flashing. You need to be looking constantly to be able to spot something that appears and disappears. Because in all cases, these things only happen once. Once they're gone, you will never see them again. So you need to get all the information you can during that brief window. So to understand all of these explosions, it's helpful to have space telescopes, but there's also another telescope that's being built that will help us do this as well. So in Chile, there is an 8-meter telescope being built called the Reuben Observatory. And 8 meters is pretty big. Here's a picture of its mirror while it was being built with all of the crew standing around it. Now this mirror is being combined with one of the most sensitive cameras that humans have ever built. And it will scan the night sky every 3 nights to try and spot things that have changed. Now we're expecting this to find on the order of tens of thousands of new objects every minute, which comes to 1 million or so objects every night. So we are soon to be in a problem once this turns on around 2025 or 2024, where we just have too much stuff to observe and make sense of, because again, we have a finite window to observe them. And if we have 1 million objects, how do we decide which one's the one we look at? So this is a big problem in astronomy where people have been working for probably decades now to make sense of all of this data that we're going to get. And that is also true here, where we're trying to help in this global effort of understanding things that change in the night sky. And the way that we're going to try and help is with the telescopes we have at OTY Mount John Observatory, where in this image, we've got one of the smaller telescopes on the mountain, only a 60-centimeter telescope, which is about this wide in its diameter. But the special thing with this telescope is that it's robotic. So you can just give it a list of things you want it to observe in a night, once the sun sets, it'll open up and go about its observations by itself. And then if the weather turns bad or the sun comes up, it'll just put itself to sleep again. So the idea is that we are making all of the telescopes at our observatory robotic, and we'll be able to use these telescopes to then try and make sense of all of those thousands of things that might be spotted in a night. Now, the reason this is pretty useful is that we are the first observatory in the Southern Hemisphere across from Chile. So as the night rolls across the Earth, things will be setting for Chile as they're rising for us. So if there are particularly interesting objects or a list of potentially interesting objects that come out of the Reuben Observatory, we can then throw them into our robotic telescopes and they'll go about their business chasing them up and kind of making a better list of things to do. These robotic telescopes are very useful because it means we can just observe every night and we don't have to go creeping around the department finding poor students and throwing them at the telescopes for weeks at a time. So another nice thing is that after we observe them, we can actually provide more information to the next observatories along the way, like the next big one at Siding Spring in Australia. So the information that we can gather can help support and make better decisions on what other telescopes should be observing. So it's an interesting time in astronomy where this one great big telescope is going to force every other telescope in the world to start working together to try and make sense of all of these things that we're going to find. But Reuben isn't the only challenge that faces us at the moment. There's another challenge that faces all of the observatories around the world, and Reuben included. And that's a very dynamic sky that's forming directly overhead of us. So for the first time in human history, we're needing to think about searching a crowded sky. So here we have an image taken by the 8 or the 4-meter telescope and the deckhand instrument, where you can see there are streaks running through this image. Now, these streaks are from satellites, in particular Starlinks, orbiting the Earth, scattering light back down into our telescope. It's only really become a problem in the last few years, and you can see why here as the number of satellites suddenly skyrockets. And what this means at the moment is if you go outside, you might see 1 or 2 satellites on a clear night at a given time. So this isn't great. It means that most of the time, or a growing number of the times, you'll start to see satellites going through your images. But if we run forward projections of what we think is going to happen, this would be pleasant because we expect there to be somewhere around 60,000 satellites by 2030. Now, instead of seeing 1 or 2 satellites in the sky at a given time, this would mean you would see between 100 to say 400 satellites at a given time. So when you next see the stars in the sky, think about how many you can see with your eye and how it would kind of feel for the majority of them to be moving. So this is a problem for ground-based astronomy because we're going to need to try and dodge and get around all of these satellites. But it's not just ground-based astronomy, the stuff that I do that's going to be impacted. As I said right at the beginning of the talk, the night sky has been constant and unchanging throughout human history. There have been cultures all around the world that have used the night sky to store information through legends and stories. But now we're in a position where just a few groups of people or a country or two have decided that they want to change this thing that has been present for all of human time. And that should be a little more poignant to us as we're starting to revive the celebrations of Matariki. So here is a time-lapse I shot from Otahiwai of Matariki this year, where we have Matariki rising, followed by the moon. And we also have some visitors along the way. And these visitors come quite close to things. So in this case, the satellite almost ran through Matariki during the dawn ceremony at Takpo. And about an hour or so later, a train of 22 Starlink satellites rushed overhead. So we're in an interesting position now where suddenly low Earth orbit is being industrialized and the sky for us is being changed. So it's always important to reflect on abrupt changes that are happening and try and make sense of, are these changes what we want to see? Are the benefits that we expect to get worth the cost? Because in many cases, it'll change our perspective of the universe. So that was a run through of a dynamic universe that plays out very, very far away from us at a nice safe distance. And then a little bit of a warning of a growing dynamic universe that's directly overhead of us. But thank you all for coming along this evening, and thank you for listening.